Okay, so good morning, everybody. For this special talk, it's my very great pleasure to introduce Dr. George Efstathiou from the Kavli Institute for Cosmology in Cambridge, who's going to tell us the latest about Planck. I don't need to really introduce George because he's such an eminent cosmologist. Everybody knows him. And I'm just going to add that he's been really central for Planck and for the Planck efforts to understand the current lambda CDM paradigm. So you're getting the closest you can to the horse's mouth here. So he will give a very good talk, I'm sure, but maybe the most interesting may be the questions afterwards. So don't hesitate to ask tough questions from George after this talk is done. Go ahead.
Thanks very much, Jan. Well, thank you for the invitation to give this talk. So, in giving a talk like this, Planck has had so much impact on many areas of astrophysics and cosmology. And it would be really impossible to, cover all of the contributions. So I've had to be very selective, and what I've decided to do is to concentrate on the core cosmology goals of Planck, what we originally proposed Planck to do. But the subtext, or the subtitle, is this. So, post-Planck, we have a standard model of cosmology. It's called the lambda CDM model. So lambda because we think that the universe is dominated by dark energy. And this dark energy, what we've learned from Planck and other data, is that it is indistinguishable to us from a cosmological constant. And cold dark matter, so most of the matter in the universe is cold and dark, and it does matter. So that defines a standard cosmology that we think, and we've argued in the last set of Planck papers, fits everything that we know, okay? But, this is research, and there are a lot of people that disagree with this. So I want to also touch on whether this standard model really does fit the data. But the core, what Planck was designed to do was to test the physics of the very early universe. So I want to give the motivation for that. So this is a space-time diagram. We're at the middle. And as we look at more distant objects, we see them at an earlier time in the universe's history. The cosmic microwave background radiation, as we go back in time, is hotter and hotter and hotter. And at a redshift of about 1,000, the universe was hot enough that hydrogen was ionized. So we call this epoch the recombination epoch. So it happened 380,000 years after the Big Bang. Okay, so what I've shown here are the paths of the photons that Planck has detected. And so at very early times, the universe was highly ionized. So the photons were tightly coupled to electrons via Thomson scattering with a very short mean free path. Then the universe becomes neutral, and the photons travel to us almost in straight lines. And the fact that they don't travel in precisely in straight lines turns out to be something that we can measure with Planck. Okay, so that's the picture. So now imagine that there's a difference in the gravitational potential here compared to here. Then photons will be redshifted out of an overdensity, and that will cause a little temperature change in the microwave background. They'll be blue shifted out of an underdensity. And so we expect to see temperature fluctuations in the cosmic microwave background in different directions of the sky that are related to fluctuations in the gravitational potential. And so, just because we see structure in the universe today, theorists expected that we would see fluctuations in the temperature in the microwave background. But there's an interesting thing, because recombination occurs, the universe becomes neutral when the universe was 380,000 years old. So there's a characteristic length scale, which is just the speed of light times ct. And fluctuations on larger scales weren't in causal contact at the time that the universe recombined. So if you see large-scale correlated fluctuations, they couldn't have been generated by causal processes. And characteristic of the Big Bang cosmology is the further back in time you go, the domain of causality shrinks. Okay, so that's what we would expect from causality. Well, as I said, theorists calculated what we would expect to see in the temperature fluctuations in the cosmic microwave background. And just after the discovery of the cosmic microwave background in 1965, people did experiments to try and detect these temperature anisotropies, but they weren't discovered until COBE flew. The COBE satellite was a NASA satellite, and it produced this map. COBE had low angular resolution, had an angular resolution of about 7 degrees. And you can see large-scale fluctuations. I mean, you can obviously see that there's stuff that's correlated over large scales. But the domain of causality subtends an angle of about 1 degree. So anything that you see here was not in causal contact at the time of recombination. So that raises the question of how are these fluctuations generated? Okay, apparently you need some process which violates causality, which is strange. So Stephen Hawking discovered this. Stephen Hawking commented that this was the discovery of the century because it requires very unusual physics. So we have an idea of what this physics might look like, and it goes under the name of the inflationary model of the early universe. So here are some of the proponents of inflation: Alan Guth, Andrei Linde, Alexei Starobinsky, Slava Mukhanov, and Paul Steinhardt. And I've shown Paul Steinhardt here prominently because Paul Steinhardt will make another appearance in this talk towards the end. Okay? So the idea is that if the universe was full of stuff that had an equation of state, P equals minus rho, negative pressure, then space expands faster than the speed of light. And so you can have a small region of the universe that is in causal contact, and then it expands, space expands exponentially, and a tiny little Planck scale region of the universe can be inflated in scale to be orders of magnitude, maybe 100 orders of magnitude or more, bigger than the observable universe that we see today. And so how is this realized? So this is the sort of simplest particle physics picture of realizing inflation, which is to say that the energy density of the universe is dominated by the potential energy of a single scalar field that's weakly coupled to anything else. And this is just a quadratic potential. And so if you start with the scalar field here, then the scalar field will roll down to the minimum, and the equation of state, if you're dominated by the potential energy of the scalar field, will be P equals minus rho, and you can realize inflation. But in addition, there will be small quantum fluctuations in this scalar field, and those quantum fluctuations can be inflated in scale and become classical fluctuations that then lead to the formation of structure. So that's the basic idea, and it gives a very pretty mechanism for solving this apparent acausal aspect of the generation of large-scale fluctuations. So that's the basic picture. So one additional thing that I want to mention is that you can have quantum fluctuations that move you downwards or upwards on this potential. And that turns out to be important in determining the large-scale structure of the universe. Okay, so when did inflation happen? We don't really know. Here is the LHC. And the LHC is probing a maximum energy of around 14 TeV. We think that inflation occurred at energies of around 10 to the 16 GeV, that's ground unification scale energies, which is 12 orders of magnitude greater than the energy scale that you can probe in the LHC. So this physics is operating at very high energies, that we can't probe directly with ground-based accelerators, but we can probe with cosmology. So that is the primary science goal of Planck, to explore these physics at these very, very high energies. And for members of the Planck collaboration that are here, the science team, here is the grapefruit. At those energies, everything in the observable universe, all of the billions of galaxies that are detected by the Hubble Space Telescope and deep surveys and so on, would have been compressed into a volume that's smaller than the size of this grapefruit. So that's what we're trying to do with Planck. And I personally believe that I showed this grapefruit physically when Planck was selected, and I think that the grapefruit really grabbed the committees that ultimately selected Planck. We also ate the grapefruit afterwards. But, so we've been really fortunate in this field. I mean, the scientific importance of understanding physics at these ultra-high energies has been well recognized. And we've been very fortunate that we've had a satellite dedicated to studying the cosmic microwave background in each decade. Okay, starting with COBE that was launched. This is my history of microwave background research, by the way. So COBE that was launched in 1989, then WMAP, another NASA satellite that produced its first results in 2003, then Planck that was launched in 2009. And maybe there will be another satellite, but it's clearly not going to come anytime soon. And in addition, and I've been unfair to all of the amazing work that's been done on cosmic microwave background research from the ground. There have been a succession of beautiful ground-based experiments as well, in addition to the satellite experiments. And at least for the next 10, 20 years, the future of CMB experimental research is going to be from the ground. Okay, so that was the COBE map. And then this is the map of the CMB that was produced by the WMAP satellite. And then here is Planck. And Planck, primary product from Planck was to produce these 9 frequency maps. So at low frequencies, these three maps at 30 gigahertz, 44 and 70 gigahertz were produced by the low frequency instrument on Planck, and then at higher frequencies at 100, 143, 217, 353, 545, 857 gigahertz, that was produced by the high frequency instrument on Planck. So Planck was, I don't want to go into the technology, and I'm not an expert in the technology, but all of these, both instruments were cooled with a very complicated cooling system, and so it was a tour de force that all of this actually worked as well as it did. What you can see from these maps is you can see the galaxy. So these are projections of the whole sky with the galactic plane running through the center. You can see that the galaxy emits strongly at low frequencies, and these two high frequencies are entirely galaxy. There's no significant cosmological signal in those frequencies. So you have a combination of synchrotron and free emission at these low frequencies, and then it becomes dominated by dust emission at high frequencies. Okay, so, and then you can see at these channels, 100 gigahertz, 143, 70 gigahertz, above the galactic plane, the signal is dominated by the cosmological signal that we actually want to measure. Now, all right, I'm going to ask a loaded question to the Planck experts. Which is the cleanest channel on Planck? Does anybody want to? No. The answer is 143. Okay, it doesn't look like it, but it is, because the dust emission on the sky is so beautifully uniform that you can easily extract a very clean map at 143 gigahertz. That's the cleanest cosmological channel on Planck. Getting the primary CMB anisotropies, separating out galactic emission from Planck, is an absolute doddle. You can do this very, very easily. And that is the cleaned CMB map, as seen by Planck, now at higher sensitivity and higher angular resolution than has ever been seen before. Okay, so I did a press briefing with the first Planck results, and caused a bit of controversy when I showed this map, and I said that many cosmologists would sell their children to get hold of this map. Some people tweeted at the time that, it's a bit bad taste to say something like that. And my wife tweeted back, because she's an avid tweeter, he has sold his children. Okay, so we produced this beautiful map. What do we do with it? Well, okay. This joke is going to fall flat here, okay? This is a picture of the sky in Cambridge. I didn't realize the weather was so bad here, okay, that it would be equally as bad, here. Okay, so that's the sky from Cambridge. Here's another picture, okay? And so if I ask, which picture has the greater information content, it's, I think, very straightforward, okay? And that's really the question that we want to ask with this map. What is the information content in that map? Okay, so here's the map. And so we can analyze this map statistically. So we can look at the statistics of 2-point correlations, the temperature differences between 2 points separated by a certain angle, average that over the sky. That gives us a 2-point function. And we can Fourier transform that and get a power spectrum. So that's a 2-point statistic. We can look at the statistics of of measuring 3 temperature differences in different shapes of triangles. That's a 3-point statistic, and it's for a transform. It's called the bispectrum. 4-point statistic is a trispectrum, and so on and so on. So that's what we do. And in this inflation model, for simple inflation models, they predict that the fluctuations obey Gaussian statistics, and in that case, all of the information content is contained in the 2-point function, okay, the power spectrum. So in those simple models of inflation, you will not detect anything in the bispectrum and trispectrum. So that's one of the principal things that we want to test. We measure the power spectrum of the fluctuations and then see whether there's anything that is detectable in a bispectrum or trispectrum, so on. You can, if there are, if the inflaton is, or what generates inflation is a single scalar field, and then, as I said, you expect Gaussian statistics, but if the inflaton interacts with other fields, then you can generate 3-point statistics, but you can generate a bispectrum and trispectrum. So, setting constraints on these higher order statistics tells us about the interactions of the field that generates inflation, if in fact inflation happened. So one of the big hopes was that if we detect something in these higher order statistics, then it tells us something about the interactions of the field responsible for inflation. Okay, so I'm going to concentrate on the 2-point statistics, and so we start with the power spectrum of the temperature fluctuations. So the way to read this is that the multipole L is the inverse of the angular scale between 2 points in radians, and this amplitude up here tells you the mean square temperature difference between those 2 points. And so it's plotted like this, so that at large scales, if the fluctuations are independent of scale, if the fluctuation amplitude is independent of scale, which is what we expect from simple inflation models, then the points will look flat. And then what you see is a series of peaks, and those are generated by sound waves in the combined baryon radiation fluid when the universe was highly ionized. And this maximum scale marks the maximum distance that a sound wave can travel in this fluid. So that's what we get, and this is what we published in 2013, and this red line here is a fit of a simple inflationary model in a cold dark matter in the lambda CDM cosmology, cold dark matter and a cosmological constant. So it's specified by 6 parameters, which I'll come to in a minute, and it provides a brilliant fit. Okay, so so good, in fact, that these kind of plots are not that informative anymore, and on the lower panel, I've shown the residuals with respect to the best fit. And just to focus on this lower panel, the individual dots are the power spectrum residuals multipole by multipole, and then this green line here is the error model, and then these blue points are just averages in bands, multiple bands, with a typical width of about 31. So this is what we published in 2018, just a few months ago, as the final legacy results of Planck. And you can see that the errors have shrunk compared to our first results. If you look very carefully, you'll see that there's been an amplitude shift which comes from improvements in the absolute calibration, our understanding of the absolute calibration from Planck. But otherwise, both the model and the data points are really very, very consistent. And it agrees really well with the theory. We haven't found any evidence for any significant deviation from this theory. So inflation in a lambda CDM cosmology works very well. So most of the work between the first data release and the final data release has been dedicated towards understanding the Planck polarization results. So polarization, so if you, in the rest frame of an electron, if it's irradiated by a quadrupolar radiation field, then that generates linear polarization on the sky. So we expect from Thomson scattering that the fluctuations, the cosmic microwave background, is polarized at the few percent level. And on the sky, we can decompose the polarization patterns into two distinct types of pattern in analogy with electric and magnetic fields. So we call them E and B patterns. So these are E patterns of polarization, and these are B patterns, curly patterns in polarization. Now, the fluctuations that make galaxies generate this E-mode pattern. So that we expect to see. And we can predict very precisely what we expect to see just by measuring the temperature and isotropies. The B-mode pattern, you need some other source to generate B-mode pattern. So gravitational waves generated during inflation can generate this B-mode type pattern. So we'll come on to that towards the end of the talk. So we can measure, now look at polarization spectra. And so this shows the cross-correlation between temperature and this E-mode polarization pattern as measured by Planck. And the red line now is, it's not a fit to the data points. It's what we predict from having measured the temperature and isotropies. And again, this fits basically perfectly. And then this is the EE power spectrum. And again, that fits perfectly, and it's not a fit, that is what we expect from having observed the temperature and isotropies. So we measured those two power spectra, but we can also measure another effect. So the photons travel towards us from the recombination surface almost on straight lines, but they're deflected by intervening matter. So there's a gravitational deflection. And we can measure that. And this is a beautiful analysis that is based on the statistics, the 4-point statistics of the temperature maps and polarization maps, actually. And so what this shows is a map of the lensing deflection potential measured by Planck. And this is quite an amazing thing, because this is caused by all of the matter between us and recombination. And the typical redshift of the deflecting sources here is a redshift of around 2. Okay? And then this is the power spectrum of this lensing potential, phi, with the Planck measurements. This is actually 2014 Planck results, of the intermediate Planck results, rather than the legacy results, just because this plot is nicer. It's a nicer plot than the other plots. This is the predictions from the lambda CDM cosmology, and then results from high-resolution ground-based experiments. So the effects of gravitational lensing match what we see. Okay, so those are some of the main cosmology results. But Planck has had a big impact on many other areas of science. We've produced clusters of galaxies detected by Planck, infrared luminous radio galaxies, the cosmic infrared background. Planck has been a great source of data for analysis of galactic emission, both at low frequencies and high frequencies. We've learned about magnetic field structure of the galaxies, star-forming regions, maps of CO emission. Planck has produced evidence of dark H1 gas with no associated or very little associated molecular gas, and so on. And in terms of volume, the number of papers covering these sort of ancillary science, if you like, dwarf the number of cosmology papers. Okay. So Planck has had a big impact over a wide range of astrophysics. Now, on the Lambda CDM Cosmology, this is a book that one of my colleagues in Cambridge wrote a number of years ago called Just 6 Numbers. And this Lambda CDM Cosmology is specified by 6 numbers. So the physical density in baryonic material, the physical density in cold dark matter, the angular scale of these acoustic structures in the power spectrum, the amplitude of the fluctuations, their spectral index, and the optical depth to reionization, which is important in actually determining the fits. So we know that the universe was reionized, it became neutral, and then at late times it was reionized from what we think from the first stars, and that is a parameter that we can actually constrain. So those 6 numbers specify the cosmology that I've shown you how well that cosmology fits the paper. So it's six parameter model. Martin called this book Just 6 Numbers. The numbers are not the same 6 numbers as these. That's one of the... we're interested in fitting the cosmic microwave background, for which this number, which is not of great significance to fundamental physics, is important. Martin replaced this by the spatial curvature of the universe. Okay? So it's not quite the same 6 numbers. Now, I said to Jean-Loup, my illustrious PI, that I would give a very slimmed down version of the science on Planck. And it would be very easy to fill in more than an hour on this number. So how do I tell you about the significance of this analysis in a general talk? Especially since, for fundamental cosmology, it's a nuisance parameter. Okay, so here it goes. It's, I think, a real tour de force of data analysis that Jean-Loup and his team were able to control systematics in polarization well enough to constrain this number. This number is constrained by the very large angle polarization patterns on the sky. And that's a very difficult thing to do because the signal is small and systematics need to be controlled on very large angular scales. So what this shows is the solar dipole amplitude for each detector at 100 gigahertz, 143, 217, and 353 gigahertz. The absolute calibration is fixed by the spacecraft dipole, the orbital dipole. And so you can measure the solar dipole for each detector, and that gives you an idea of your photometric accuracy. And because Planck measures polarization by differencing signals in different bolometer orientations, you need real high precision in the photometric calibration, the detectors. And so what this shows is that the RMS photometric accuracy at 100 gigahertz is 5 times 10 to the minus 6, then 9 times 10 to the minus 6, and then it degrades as you go to the higher frequencies. So, so the systematics have been controlled at a level where the photometric accuracy of Planck is an order of magnitude higher than the Kepler satellite, which is an amazing achievement. And so that's how we can get measurements of the optical depth of reionization, and then we can convert those into constraints on the redshift at which the intergalactic medium was ionized. And so these are the constraints that we've published in the 2018 papers. Our universe was reionized at very late times, and that fits with a lot of other observations of the properties of the intergalactic medium. Okay, now I wondered whether it was worthwhile putting this graph in, because this gives you numbers. So the 6 parameters of the model, which I would really have to define in a lot of detail, and I'm sure you don't really care, plus derived parameters, so the Hubble constant, the density of matter in the universe, the amplitude of the fluctuations, and so on. Okay, so I'm not going to bother doing that, except to say that the results are very consistent between temperature and polarization, and the precision of these numbers is now so high that really cosmologists don't care about it anymore. Okay? So you could conclude that cosmology is done, and so on. Okay, so, but that's not where the field is. You know, back in 2013, when we published the first Planck results, the parameters that we derived were, you know, very consistent with our own measurements of the lensing of the cosmic microwave background. So, and it would have been a disaster had that not been the case. They were consistent with galaxy surveys, which can also measure this the acoustic features in the galaxy distribution, so-called baryon acoustic oscillations. But we were in disagreement with cosmology determined from type 1a supernovae at around the 2 sigma level, so, you know, sort of marginal disagreement. We were quite inconsistent with direct determinations of the Hubble constant. We had tensions in measurements of the amplitude of the fluctuations from weak lensing observations of galaxies, counts of clusters, including our own counts measured from Planck, and with other estimates of the amplitude of the fluctuations measured from galaxy surveys. So when we published that paper, we were basically in disagreement with most of the rest of cosmology. So it was quite a brave thing to do, and it generated a lot of interest in the cosmology community. So what has happened since? Okay, in the 2018 results, we have very good consistency with lensing measurements of the CMB. We have beautiful consistency with galaxy surveys. That disagreement has disappeared. So we're consistent with supernovae. This has got much worse. Okay, so Adam Riess and collaborators have a campaign for measuring the Hubble constant, and now this is in 3.8 sigma disagreement with what we measure from Planck. Then these other things, in the 2018 papers, it's not clear whether we're consistent with weak lensing galaxy measurements or with cluster counts, but the distortion of galaxy clustering statistics in redshift space is consistent with Planck's. Okay, you know, some people periodically doubted the fidelity of the Planck data. Maybe the reason for these problems is because of some residual problem with Planck. Well, it's clear that in 5 years, we've just doubled down, you know? We're saying the same things that we were saying in 2013, and that's after 5 years of, you know, really close scrutiny of the Planck data. We can't see anything wrong with the data. Okay, so again, it would be an entire lecture to go through even a few of these tensions. So I've decided to just say something about this. This is the most discrepant thing. Okay, so as I said, if you measure galaxy surveys, you can detect the impact of sound waves in the structure in the galaxy distribution. So this is shown here from one large redshift survey. So you can see acoustic peaks, and so what you can do with you can measure these acoustic peaks from a galaxy survey. You can measure them along the line of sight, which gives you a measurement of the Hubble constant at the redshift of the galaxy survey, or you can measure them perpendicular to the line of sight, which gives you a measure of the angular diameter distance at the redshift of the galaxy survey. So if you have, so it gives you these measurements, but you need an absolute calibration. So you need to know the physical length scale to actually convert them into physical units. So that physical length scale is set by the distance that a sound wave can travel in the baryons, and it just depends on the matter content of the universe. So it's very well constrained in an almost theory-independent way from the cosmic microwave background. Okay, so the traditional forward distance ladder measurements work on a complicated chain where you have to have distances, absolute distances to nearby objects, say from Gaia, or from looking at other things like the Mega Mesa galaxy NGC 4258, that establishes a distance of nearby objects. You then use the period luminosity relation of Cepheids in galaxies which once hosted a type 1a supernovae, and so you bootstrap to the distances of these supernova host galaxies using Cepheids, and then you match to the supernovae magnitude redshift diagram and extrapolate out to large distances, and that gives you the Hubble constant. So that's the traditional forward distance ladder approach. But nowadays we can do something else, which is that we can do an inverse distance ladder working backwards. So this has been done by many people. These are results from a recent paper that I wrote with my students. So the inverse distance ladder, we make an assumption about the absolute scale of the baryonic sound horizon. And then these are the measurements, direct measurements of H of Z from galaxy surveys, from studying those acoustic peak structures in galaxy surveys. And then you use the type 1a magnitude redshift relation from supernovae, and that constrains the behavior going down to the present day for any form of this is really theory independent. So what's done here is that we've chosen just a parametric form for h of z, and then fitted the parameters to the data. And the data is now so good that this is how well constrained things are. So the way to think about this is you make an assumption about the baryonic sound horizon. That gives you h of z properly normalized from galaxy surveys, and then the supernovae limit the slope extrapolated to low redshifts. And that's the Riess point. So, so this discrepancy between the forward and inverse distance ladder measurements is nothing really to do with the Planck measurements. You can use the WMAP measurements and so on, or you can use non-CMB measurements, just the agreement that Big Bang nucleosynthesis is enough to give the same result. So here's what you get doing this for two different values of the baryonic sound horizon, either from Planck or WMAP. Here are the Planck results on H0. Here are the direct forward distance ladder measurements. So there is a discrepancy. It's not specific to Planck. And there's a consensus now in the field that to get out of this, if it were real, if there isn't a problem with the Cepheid distance scale, then you need new physics that changes, that lowers the value of this sound horizon by about 10%. That is a very difficult thing to do. So that's where we are. Okay, now the 6 parameters defining the lambda CDM cosmology, they fit the data, but there's another parameter that there's very good reason to have another parameter in an inflationary model. And if the energy scale of inflation is high enough, then you would expect to see gravitational waves of high amplitude. And there was a lot of excitement when, a few years ago, when the BICEP team published this beautiful picture of B-mode anisotropies detected in, their field of view is about 2,000 square degrees. And they had clear evidence of a B-mode signal. And they announced the possible detection of gravitational waves. So this got a lot of media attention. And if this were correct, it would have been the first time that an intrinsically quantum gravitational phenomena had been detected in nature. Unfortunately, it wasn't caused by gravitational waves, and members of the Planck team more or less instantly realized that in that region of the sky, polarized galactic dust emission was high enough to explain what the BICEP team saw. We then collaborated with the BICEP team. The best way of getting good constraints on galactic dust emission was to cross-correlate their high sensitivity data with the less sensitive Planck 353. That improves the sensitivity to galactic dust. And when we did this combined analysis, there was no evidence of any primordial gravitational wave signal. The entire BICEP signal could be explained by polarized galactic dust emission. So this is very important for setting constraints on inflationary models. So when you are dealing with physics that is at such high energy, theorists have a lot of latitude. And so there are many, many different types of inflation model. And this slide is the first of 5 slides that was produced by my colleague Paul Shellard at the Department of Applied Maths and Theoretical Physics. And all he did was look at the titles of papers, any paper that has inflation in the title, and just arrange the inflationary models in alphabetical order. And it just keeps going on and on and on. So there are many different inflationary models. Okay, so here are constraints from Planck with some of those models, and I'm not going to go into details over the types of models. But what this shows here are the constraints on the relative amplitude from gravitational waves to scalar fluctuations. The scalar fluctuations are the fluctuations that make galaxies. Over here, so against the spectral index of the scalar fluctuations, which Planck measures very accurately. So the constraints from Planck combined with the bicep data constrain you to ellipses that are here. So the tensor to scalar ratio is lower. This is the 95 percentile upper limit. You have to be less than about 0.09, 9% or less, with no detectable evidence, no evidence for any gravitational wave signal. Okay, this rules out a large number of inflationary models. It also allows a large number of inflationary models, but it rules out a large number of inflationary models. So here we go back to Paul Steinhardt, because this is a Scientific American article that was written by Ilias, Steinhardt, and Avi Loeb, and say the latest astrophysical measurements combined with theoretical problems casts doubt on the inflationary cosmology. Now I've just shown you an inflationary cosmology fits everything to incredibly high precision. And these people, who are intelligent people, are looking at the same data and saying inflation is in trouble. Okay, so how can that be? So this article came out in Scientific American, annoyed quite a few of us, and we wrote a letter to Scientific American. Right, so the reply from a group of 33, of which was probably number 32 or something. So we wrote an article saying why we didn't agree with their interpretation of the data. And they wrote another article, another reply to our reply, saying why we were wrong, and at that point Scientific American says, shut up, we're not going to publish any more on this, okay? So how can people look at the data and come to such different conclusions? So I've got like 3 minutes to explain why. So in that original sort of picture, a simple model of inflation where I drew a parabola, the idea is that we have some, power law-like inflationary potential. And if we write the potential as just a single power law, then the spectral index is set by the parameter alpha, and the tensor to scalar ratio depends on the parameter alpha. Lambda determines the amplitude of the fluctuations, and then this number n is the number of e-foldings that you need inflation to last for, which is a little bit uncertain, but we can calculate this, and you need 50 or 60 e-folds to make an inflationary model work. So given what we measure from Planck, then we would have expected to have seen, or had alpha of about 2.2, which would have given us a detectable tensor component. We would have detected gravitational waves in that model. So that doesn't fit the data. This kind of simple one parameter, or at least very simple natural model of inflation doesn't fit the data. So we need a more complicated model, and the way that inflationary phenomenologists work with this is in terms of slow roll parameters. So epsilon just depends on the first derivative of the inflationary potential with respect to the scalar field. Eta depends on the second derivative, and so on. And to get a successful model of inflation, these two numbers have to be small. And so in terms of these numbers, I can get the spectral index, the tensor to scalar ratio, and the spectral index of the gravitational waves. Well, we know this is small. So epsilon is small, which means that eta, this parameter eta, is much bigger than epsilon. So in inflationary model building, the parameters, we now have a hierarchy problem in the parameters of slow roll inflation. Okay, so the theory is more complicated theory that involves a hierarchy of parameters that we don't understand. And now going back to the criticism of inflation, this is sort of paraphrasing their argument. Imagine that we have a potential like this, then we don't have inflation here, we have to have inflation here, where the inflationary potential is unusually flat. And so if inflation starts here, it runs for a limited number of e-folds, and then inflation ends when you hit this minimum. If you have inflation up there, it doesn't fit with the data. But you generate huge amount of more volume if you inflate up here than you do up, here. I can arrange for, many, many e-folds of inflation. So if you now imagine that you can have any potential that you want, any shape of potential, why does inflation start there rather than up there, where you're rewarded by many, many more e-folds of volume? And the problem is even worse than that, because the fluctuations, as I said right at the beginning, introducing inflation, you can have fluctuations that move the influence on potential upwards. Up on in the upward direction, and that gets rewarded by a large number of e-folds of expansion. Upward fluctuations are rewarded by increased volume. So inflation never ends. Inflation is eternal. So that's the picture that we have of an eternally inflating universe in which little pockets, inflation ends in little pockets, and we don't know where this potential comes from, but what we actually measure is a potential which is not heavily rewarded by large e-folds of inflation. So, is inflation the right theory? Are these people right? Well, I think the answer is yes, in the sense that inflation is an incomplete theory. We don't understand the initial conditions of inflation, and there is a problem with predictability in this infinite landscape of eternal inflation. But I think they're wrong. That doesn't mean that inflation is in trouble. It just means that there are many, many open problems in cosmology. And we should acknowledge this when we talk about inflation and teach inflation. Okay, so what is the most important legacy of Planck? Lambda CDM is not fake news. there is no convincing evidence for any deviation away from this simple 6-parameter cosmology. Okay, so there is, I think almost certainly intrinsic truth in this model. Any deviations are very small. But we really now need to look at these other issues, because these are important problems. Are there any viable alternatives to inflation? There's no theory that is on an equal footing to inflation. But what sets the initial conditions? How do we deal with the problem of predictability in an infinite landscape of an internally inflating inflation? Are there signatures from a pre-Big Bang phase, and so on? So a lot of fundamental problems that remain to be answered. So I'll end this. My assessment of Planck is that it's been very important in establishing the standard model of cosmology, but it has features that we don't understand. And if you actually look at it, we've measured parameters to great precision, but we've measured stuff that we don't understand to really high accuracy. We don't know what the cold dark matter is. We don't know what the dark energy is. Maybe it's a cosmological constant, maybe it's something else. We have these important fundamental problems with inflation. And so I really believe this, that the field has now got to a point where, this quotation, it's not the end of cosmology, as some people have actually said to me, you measured all this stuff. That's not the end. It's not even the beginning of the end, but it's the end of the beginning. So we've now got to focus on these big, big questions. And I only have 3 years until I retire, So I'd just like to thank all of my collaborators. It's been an amazing, collaborative effort to get all of these results. And so, yes, so I'm grateful to everybody who's contributed to Planck. So thank you.
Well, thank you, George, for a fantastic talk. I hope you all enjoyed it as much as I did. It's late, but we should have a few questions, I think. So who would like to start? Come on.
George, this is in a sense a philosophical question in the list of 6 numbers. Why is T0, the temperature of the CMB, never included?
Well, because it's very, very accurately measured. Okay. No. In that sense, it should be included. But it's very, very accurately measured, and it wouldn't affect our fits for the other parameters. But yeah, you're correct.
Okay. It's only the experts asking the questions here.
George, we all know that when we think about an unknown world, what is really important is to define observables. Mm-hmm. As an experimentalist, I agree on all the points you have listed in your last slides, but which are the observables to get the answer to your questions?
Oh, right. So this is, I've had many sleepless nights worrying over these problems. I mean, the key criticism from Elias Steinhardt and Loeb is that this measure problem, internally inflating multiverse, means that we can't predict anything. Okay, because we don't know how to apply a measure. Okay, so inflation is intrinsically can predict anything. And in a certain, it's true. I don't know if you remember a while back, there was, inflationary theorists, were being browbeaten by observers claiming that the universe was open. Okay, this is in the 1980s. And so there was a period where people were making inflationary models that gave you an open universe. Okay, so you can do that with fine-tuning. So if we turned out, if we get limits on gravitational waves at 10 to the minus 4, which is fanciful, as things stand, could I make a model of inflation that fits? Absolutely. So anything, you give me anything, I can make a model of inflation that fits. Okay? And so inflation is not a proper theory. It can explain anything. Okay? Now, I think that just means that we don't understand the physics of inflation. Okay? This is where we are.
Okay, here's a question.
Thank you for a lovely talk, George. I'd like to ask if in the future there is like a successor to Planck, another CMB mission, what improvements would you have on that mission?
Okay.
He's a theorist.
All right, I'll answer this with a true story. This is a true story, okay? Maybe slightly embellished, but it's basically true. I was asked to get involved at a very early stage as a theorist, to provide some guidance to the experimentalist. So I sat there in a meeting, and there was a lot of discussion of, instrument designs and so on, what we might actually build. And then they turned around to me and they said, so what do you think we should build? I just said, well, I think you should build something which covers the widest frequency range that you can, with the highest angular resolution and the greatest sensitivity. and then instantly, internally, was saying, you stupid idiot. What a stupid thing to say. And my experimentalist colleagues said, thank you very much. And then they invited me to the second meeting. so the answer to your question is, how much money have you got? Okay? That really, anything that, my assessment, to do something which produce a major improvement from space, you have to build something that's very expensive, okay, to compete with what you can do from the ground. And the only other thing that you could do is to gamble and produce a low-cost, low-resolution, but with very good control of systematics, satellite to go for the tensor modes from space, and tau. And I'd be prepared to gamble and make it low-cost, making assumptions about what the foregrounds are like, and so on. So those are the two approaches: super expensive, or very restricted science goal, as cheap as you can make it. And then the problem is that if it's very restricted science goal, then how do you convince the rest of the science community? Tensor modes may be important to us as cosmologists, but if you're a solar system scientist or whatever, are you grabbed by that? I don't think holding up a grapefruit is going to do it. Mm-hmm. Okay.
So here's one last question.
Yeah, thank you very much. I think you almost answered it, but I was wondering, what does it take and when will we actually observe primordial gravitational waves?
Okay, so from the theory point of view, we haven't a clue. Okay, and don't believe any theorist who says that they have a clue. Okay, the ratio of the tensor to scalar ratio could be down at the 10 to the minus 10 level for all we know. Okay, so we don't know from the theory point of view. But the best prospect is from ground-based sensitive ground-based measurements now for, extensions to BICEP, the BICEP Keck experiment, and just pushing down to that. And maybe we'll be lucky. Okay, it's definitely worth doing, because if you do get a detection, then it means that the inflation scale is high, energy scale of inflation is high, and give us a big clue to what's actually going on.
So last question to Chris.
Hey George, so I was rather surprised, I have to say, that you didn't quip about that we don't know anything about the nature of cosmological constant or dark energy. Likewise about dark matter. These are significant and important components of the standard model. That's what we have to believe. You've been personally invested for quite a long time with dark matter studies. Cosmological constant became reality in the 90s.
Yeah.
You're now, as you intimated, close to retirement. How do you feel about that? What are the prospects? What's the intellectual trajectory to take here?
Right. Okay. I mean, it would take quite a long time to give you a proper answer. An answer which has more intellectual depth than my comments on how to design, satellite mission. So, look, these are pressing problems. Okay, what we've learned from LHC is, WIMP miracle and all of that sort of stuff, right? I mean, there's probably nothing in that, okay? And that dark matter is more complicated than we thought. On the cosmological constant, there has been no significant theoretical development on that for a long, long time. We haven't a clue.
So on those words, I think a fitting finish. We haven't a clue. Let me just say that we are starting a day and a half Planck meeting this afternoon, so you have a chance to ask questions to George, but also many other Planck people who will be walking the corridors for the next day or so. Let's thank George once again for a fantastic talk.